Hey, Russell, how you doing?
Doing good. How about you?
I'm okay. Who else is in the? What other folks do we have joining us remotely today? So we have Amelia. And Jose, good to see you, Jose. I need to email myself the slides because. They wiped everything off this computer, so I lost all my. Tools, which wasn't much, but it's still annoying. Hopefully we don't have, knock on wood, we don't have a huge equipment failure today like we did, or like I did earlier. Anyway. All right, so a couple of bookkeeping points. I will not be here next week or the week after. I haven't looked at the current email chain. I believe there is a sub for next week. The week after, you will be taking an in-class exam. So what's that, the 6th? So the 30th, there'll be a sub. If the sub doesn't work out or did we finish 3.5?
Sure. I don't think so. We have an example.
Did we do any examples?
We have one, I believe.
We did one. Later, I guess, just, I don't see a problem. All right, so let's see if we save those notes so we can see where. Oh, now they're all back. Who would have thunk it? Yep, I have a note that I need to finish this. Okay. So we will start there. So if you don't, what I'm thinking about doing, and let me know if you want to go on the front end or the back end. I know this won't work for everyone. Since you have a sub next week, and I don't know. Well, first off, I'm not sure if you have a sub, but I'd like to make sure you get your full, paid for your seat time. I'd like to make sure you get it. So my thought is would you prefer to start the class 20 minutes early or run 20 minutes late?
Early,
Early?
early.
Okay, all right. I don't think you're supposed to be seeing anything yet. Let me turn that on. Can you hear me? All right, so camera is not turned on. Let's fix that. Go. Let's suck it in. Show what the preset is in this room. And let's go ahead and share. All right, so thank you, Amelia. Are we in good shape now? All right, so those of you that are here in the classroom, this was sort of my game plan, for lack of a better word. I went ahead and I have written up and I guess we didn't get to non-uniform torsion either. Correct? Did we? I thought we did it for some reason. So you guys told me that. Yeah. Okay, so we need to get in and do some of these problems. Right, am I correct? Simon, where did we leave off? You're in charge. You're officially in charge today.
We left off at doing the example of 3.5-3 for section 3.5. That is what I have last.
3.3. 3.3. So we completed this.
Yes. Three 5-3.
And I'm wondering if we lost that,
Is it?
oh yeah, 3.4.
Thought it was just. Here's my. So maybe.
Okay, so we did this. And see if there is, the problem is at the end of this. So this was 3.4.4. I wonder where the 3.5 notes are. See if they're in the download folder. 230, 3.4. And 3.8 is what I just downloaded. Or did we just pull that as an example? I'm sorry, I'm being disorganized and now I'm getting very embarrassed.
Can't remember.
Okay. I stopped sharing. I'll reshare in just a moment. Once it opens up. Okay. All right, so we were doing pure stress and strain. And Is this where we left off, or was it where we left off?
It's that one right there.
353, excellent. All right, thank you. I appreciate your help with this. Anyway, back to before I got myself completely turned around and distracted. So, can you see my screen now?
Yes.
All right, good. All right, so we have the right screen up. Everyone's seeing this particular example. And let's go ahead then and work through this example. And I think I grabbed the wrong ones. I have for you a, I was gonna plan to do a quiz on 3.4. I have a pre-class quiz for 3.8, and then I haven't posted it on D2L, but I have a proposed review lecture. Okay, and that might have to change, depending on what happens, but for your exam in 2 weeks. And so I went ahead and I did that up this afternoon and brought it in, just in case. I don't have a sub for next week, right? Your take-home exam is due today, right?
Yes.
Okay. And hopefully you've had a lot of fun with that.
So much.
Good. Did you learn something?
Yes.
I did.
Good. Then it was worth it.
I had fun looking up all.
I learned how to cry with no more tears.
While you're dehydrated?
Dry cry.
Dry cry. It's ugly.
Okay, did anyone head over to U of A?
Yes.
And did anyone head down to Pima?
No.
No.
Was U of A valuable?
Yes.
Yeah.
Good.
Stuff going.
A lot of good stuff going on?
Yep.
They were telling me they were talking to somebody. And they were only interested, oh, Pima County is looking for civil internships for civil engineering this summer.
They were at the mining event?
No, they were at the U of A, they were at my event, they were at the Pima event.
Oh, okay.
So just as a heads up. I want to check out their website. Did you get any good leads down at the mining event?
Sort
A
of.
couple.
All right,
We went pretty early. They're still kind of setting up.
I thought it was at start at 9.
That's what we thought too.
Oh, when does it start?
9:30.
9:30 apparently.
Sorry about that. I just forwarded, we can all blame Alex. Yeah, Alex, I saw the email and the answer is yes. All right, but y'all can blame Alex because I just forwarded what she had forwarded me. But who said mining people were organized?
Everyone at the events sounded confused too. They were like, wait, when does this start?
Yeah.
I heard a couple people like, wait,
10:30.
10? 9:30? 9?
Well, I do know from Wednesday's event, I was told by multiple people that Pima County is looking for civil interns this summer. So you might wanna get on their website and see what they have, but they are definitely looking for civil folks. What'd you say?
So I wonder if I'm gonna have a summer.
Or if you're gonna be grinding.
Yeah.
What you be doing?
I have all my arts and humanities.
No.
It's gotta do art class, bro.
He has all those what?
I have to do arts and humanities still,
Oh,
like all my life.
come stop by mining on the mall tomorrow.
Yeah, they're doing a jack leg on a big ass rock tomorrow.
Oh, okay. Well, I think you should definitely go for that. That's fun. We used to have back in the dark ages,
Yeah, like old school drilling holes.
old school drilling holes.
Blast powder dynamite for mining.
So they drill a hole.
Yeah, but it's really cool and loud and stuff.
Yeah, it's super loud, it's super cool.
Yeah, what he said.
So my undergraduate degree is in car school mines, and we used to have what they called engineering days, and people would compete with stuff like that.
Yep.
I think they probably still do have it, but, all right,
Yeah, nobody got treated. So, competition.
okay, let's go ahead and dive into this problem, because Cade likes to do problems. He doesn't like it when I talk about theory. All right, so we have a hollow aluminum shaft with an outside diameter of 4 and an inside diameter of 2. When twisted by torques, the shaft has an angle of twist per unit distance equal to 0.54 degrees per foot. Shear modulus is given to us in PSI. So you can probably already see that we're gonna have a unit issue, correct?
Yeah,
Yep, anyone else see that there's a unit problem going on? So let's try to break some of those unit problems down, and then we'll go ahead and determine the maximum tensile stress and the magnitude of the applied torques. All right, so we have D is in inches. My problem that I'm seeing, I don't know if you guys are seeing it or not, but V, I have V as 0.54 degrees. So in my opinion, that one's a bit of a double whammy. Do you agree? Degrees per. Oh, Robbie's competing. Well, then everyone needs to go. Robbie's competing.
you can-
All right. 0.54 degrees, and this is per foot, which is why we have a problem. So first thing we need to do is we need to turn this in to radians. And we need to turn the feet into inches. All right. So the answer I have here is pretty funky, but 785, I think we got something close to this, didn't we? 0.4.
To do the -4 rads per inch,
Okay, so you still got 7.85.
yeah.
Excellent. All right, so do we have, I guess, enough information now to figure out? Well, ultimately, we want to figure out our sigma, but I believe for this case, our tau max is then going to equal our sigma max. And the equation for our tau max is then G R phi.
B or theta?
Is it theta or is it twist angle phi?
That is a good question.
Oh, it is. No, it is the angle of twist per unit distance. All right, so we have all these pieces and we can plug this in.
Yeah, because we just found theta, right?
Yeah, we just found theta. All right, now let's talk about the structure. Okay, we have an inner diameter and we have an outer diameter being 4. And when we've discussed this, where are we going to have the most torsion occurring?
Outside.
So
On the outside, right? As we go inside, that R basically goes to 0. So we're going to use that outer diameter. So we have our G that's given to us in the problem. And we probably, oh, it's PSI, we're okay. we have diameter, so that's gonna be 4 divided by 2, right? And then we have our angle, 785 times 10 to the negative 4 rad per inch. Okay, and you plug all of this in, those inches go away, and I'm seeing an answer of 6238 PSI. Is that what we got?
I got 6283.2.
Oh, you're right. Right. Now, when we're on that 45-degree plane, I kind of wrote this down, but I didn't like talk about it. But when we're on a 45-degree plane, right? That's a magical space for us because the tau max is then going to equal the sigma max at that point. All right. If you remember, your sigma is coming in here, right? Your tau is there. If this is at 45 degrees on that plane, then those two are both going to be, at 45 degrees, are going to be the same. Okay. So we're then able to say, because we're on the 45 degrees angle, so at the plane at 45 degrees, we can then say our sigma max equals 6283.2. All right. So at this point, what do we want to find for part B? Determine the magnitude of the applied torques, right? So we're looking for T, aren't we? Do we have a relationship between torsion and torques?
Yeah.
Yeah, we do.
Tau equals TR, right?
Excellent. So tau equals TR over IP instead of J. That annoys me. So IP, now, when you do your in-class exam, right, this table will be given to you. In fact, I think it was on your last exam by accident, wasn't it?
The table, yes. I believe
Yeah.
so.
Yeah. So we have a hollow pipe, so that's going to be pi over 32, right? And then we're going to have our outside diameter minus our inside diameter.
I think. Yes, diameter to the fourth.
Oh, it's to the fourth, it's not
Yes.
squared. That's right, because it's a moment of inertia.
So
So,
the hollow to
Length.
no whispering today, because my hearing, I didn't get my hearing aids in. So, what is our answer on this?
I got 74,000 pounds inch.
Whoa.
Oh,
no.
I'm sorry, IP.
Yeah,
Um,
maybe 23.
23.562 inches to the fourth.
Right, inches to the fourth.
Inches, what is that? Inches. Quad inch.
All right, so now we can go ahead and we can figure out our T by doing some rearranging. So we're gonna have tau IP divided by R. No, I don't think we need a quadratic equation.
No,
Equals
what is something like inch to the fourth? How can you say that differently? Like
Yeah,
quad
like
inch?
square and then cube and that like.
Yeah,
Fourth is just to the
so is
fourth.
it just to the fourth?
It's just to the fourth.
Oh,
Trying to be fancy.
I was.
You were, well, you're fancier than I am, let me put it down. So we found that our tau was 6283. All right, we found our IP, and let's check our units here. So this, we found this is in pounds per square inch, right? We are then going to have 23.5 inches to the fourth. That's gonna be divided by the outside diameter. So that's gonna be 4/2, and that will then be in inches. All right, so we will then end up with 60, or not 62. You told me what the answer was, what, 7,000 something?
74,000
74,000.
pound inch.
Units are gonna work out on that, which is good. Okay. All right, should we do the next one? What do you think?
I'd say we should move on to the next section.
Move on to the next section?
Yeah, I'm very tired of looking at all these T's.
Well, we're gonna look at them for a little bit longer.
Just you wait, my friend.
Here you go. All right, so let's go ahead then. We're gonna talk about how we use these lovely teas that we've been working with. All right, and I know my civil and probably my mining people don't care much about this, but it is a course objective. So let's see if this is one of the ones that I downloaded. And the answer, of course, is no. Because we're having one of those days. 3741. All right. Let's go ahead and do this one first. I just think it makes a little bit better sense. And then we'll talk about power and move into chapter 4. So I'm going to stop sharing and reshare once it opens. It is open. Okay. Right now we have the infinite mirror going on, which I personally find very annoying. I don't know if you guys enjoyed those in fun houses or not, but I did not.
It's fun.
It was fine.
It was fun.
It was fun. Okay. All right. All right, so let's go ahead and we're going to talk about statistically indeterminate. And as I said, I'm bouncing into 3.8 and then I'll come back to 3.7 and we will talk about power. And that then will lead us into chapter 4. So this is, it says the title I wrote up here is statistically indeterminate. We've already solved those, haven't we? But we're going to learn how to do it with torsion members. Okay, when we see the word statistically indeterminate, what does it mean?
It's not moving.
Okay, it's not moving,
Uh,
not quite. Not quite. So what do we have?
2 reaction forces.
We do. We have our pipe in here and then we have 2 reaction forces. Oh, by the way, I know this is a squirrel moment, which really, it pisses off Simon when I have these. There is a chapter about beams and beam design, and I'm going to have you guys do a little project on that chapter. So I will get that out to you in case you want to get started on. Okay, so what happens when we have statistically indeterminate? It means that what? We are being locked in on 2 sides, correct? How did we handle this? Not sure what these.
Oh, we cut one of the walls off.
We cut one of the walls off. So previously, I can't remember the chapter off the top of my head. What's the chapter? Simon knows.
2.3.
That sounds good to me, but I don't know.
It was,
No, that's changes in length. Condition.
It's definitely in chapter 2.
It was in chapter 2. All right, so what did we do in chapter 2 when we had a situation like this? Well,
2.4.
2.4,
Yeah.
right? So we removed one of those walls, didn't we? Okay, so if you remember what we did at that point, we removed we removed a wall. All right, and then with the free end, what did we calculate back in chapter 2?
It's the reaction forces, right?
We could, but okay, so yes, the reaction forces. So we summed forces, correct?
Yes.
But we had to have another equation to be able, when we put the wall back on.
Oh, your delta,
Right, the fact that the deltas, because there were two walls. Now, remember, delta was then what? It was our expansion. Or elongation. That's a better word.
oh, delta's,
Right?
That was.
So what we then did was we said, well, when we put the wall back, right, if this is delta A plus delta B, it's gonna have to equal 0. All right, because it's not actually free. And so that was there's this particular word for it, compatibility equation. So we were able to solve this because we had this compatibility equation. All right. So that's what's happened, that we've already done these types of problems. The difference in 3.8, we're gonna do it sort of in parallel. Can I change slides? Give me a 2 if I can change slides. What time is Robbie competing tomorrow? I wanna pop some popcorn at 10. Yeah, that's when that meeting is. I have a meeting to go to, but I'm gonna pop popcorn and watch it, the you know what fly.
you bet.
He'll be competing at 10 it starts at 10, but he'll be competing at U of A. So,
So your meeting
no, my meeting starts at 10.
after you bet.
No, it's at here at Pima. Or around that time. Yeah, well, it's the mining department. Could be 10, could be 10:30, could be 11:15.
We're very confident.
Could be after we've had 4 beers. Maybe we need 5 beers, then we can get started. Oh, I am just, Alex, it is fine, don't worry about it. Honestly, it truly is the mining industry.
Gotta drink.
Don't take it personally, Alex, not allowed. Are you tired, worn out? Okay, so let's talk about how to solve this now when the bar is in torsion. So we just did a problem where our bar was torsion and it had torque and it had radius and all that type of stuff. And we're going to do this very similarly in the sense we're going to start by removing the wall or removing a support. Oh, Robbie's taking it personally. Oh, well, that's okay. All right, so Robbie, don't take it personally. Okay, as I said, 10 o'clock tomorrow is when the meeting here at Pima is. All right, so what are we gonna do, right? We're gonna go ahead and we'll start off with our, remove the wall, and then we'll move into our free body diagram. I didn't write that on the last one, but that should already be entrenched in your brains, right? Once we're done with our free body diagram, we summed forces on the last one, didn't we?
Yeah.
Okay, what do you think we're gonna sum now? We're gonna actually sum up the torques.
More teams. Awesome.
Okay, torque is applied externally, right? Torsion is then what is going to happen internally. All right. Okay. Now, once again, we need what? We need that complementary or compatibility equation. Right? In chapter 2, we were dealing with delta. So we were putting forces on stuff that was being elongated or shrunk. Now we're dealing with torque. And so now we're going to have the angle of twist involved. Okay. So that's how we're going to go about solving these problems. So let's go ahead and do an example. All right, let's see. So what do we have? We have just random word example. It's okay. How bad is the one we are doing for class?
What case would this be applied to in real life? Just out of curiosity.
Well, so where you would worry about it would be if you have something that's being twisted. Primarily when stuff is being twisted, which is the next section, we're trying to produce power. So your drive shaft, right, that's going to rotate in your car.
Right.
Or at least it used to. I don't know what happens in cars now. But your drive shaft will rotate. So it's constantly under torque, isn't it? So the purpose for this class is, when is that going to fail?
Okay.
Okay, and that's what this class worries about is, and we don't actually spend a lot of time with failure analysis, but that's really what you need to think about. You need to think about with this, can this material and this, structure with this diameter, can it handle this torque? Or is it just gonna go and twist all up? All right, I'm trying to think from a civil engineering point of view where you're gonna see torque.
Support bracing for buildings,
Yeah.
settling.
Not only building, settling, I was actually thinking wind. In your high rises, how you might get some wind shear and you might get just, and it doesn't take a lot, but you might just get a little bit of torque from wind shear. What about mining? When do you guys have to deal with torque and torsion in mining, Alex and Robbie?
That's good.
What'd you say?
So drill, baby, drill.
Drill, baby, drill. So yeah, in their drills and blasting, not the blasting, but definitely in your drills. Okay, that's why you'll have to take geomechanics. Because depending on what you're drilling, measuring rock properties, okay. Yeah, the other thing is, depending on what you're drilling, that might then dictate your drill bit, so to speak. What'd you say?
Just reading.
Blast patterns. Okay,
That is so.
right, and the other thing that they have to worry about with regards to that is so I would like to do this example and then we'll do the one out of the book. The one out of the book refers to a couple of equations, but I want to do this example so we can walk through it. All right. So and sometimes you have to think out of the box. So I'll give you a real life story. Husband was working for a mine and they needed something to pull, I think it was in the tank house, and they were worried about the sediment in the tank house. All right, and they were trying to mix it up so they wouldn't have so much sediment or something of that nature. So if you think about it, all right, you need to mix up something that's in acid. You guys have gotten some basic materials. What do you think he found to be able to do this?
Wait, to mix acids,
Yeah,
air.
no, they didn't use air.
Oh, yeah.
Water.
People
No,
would.
they were trying to mix the particulate up.
With
So they
some
can
sort of
float it out.
steel, right? Some sort of metal,
It is a metal, but acid will eat steel.
so. aluminum.
So if you're doing aluminum will break really easily on you.
Yeah, but it's just fluid. You're not mixing it that fast.
So really what he actually came up with is they make titanium propellers for racing motorboats. And he used that, he put that in the tank house. So, you know, sometimes you do have to get outside of the box a little bit. I thought that was clever that he did that. But then again, the man got a patent for a bent wire, so we're like, whatever.
For a bent wire.
Yes,
Really proud of that one.
no, I just think it's so funny, so I actually paid for the big plaque. He has a lot of patents, but the bent wire one is the one that I thought was just hysterical, that actually went through. And it wasn't the fact he bent a wire. Anyone can bend a wire. It's the fact he used the wire as a tool to repair a generator on a fixed wing aircraft. And so now it was a new use for a bent wire. And it's a very complicated title, but reality is it's a bent wire. And he literally, I think military, I think he was at a military base. They were trying to figure out how to get to something. And my husband, being my husband, just bent a wire and went in and went, oh, that took care of it.
It's like the 2001 Space Odyssey scene. Like, no one. Okay.
You gotta give me more context, it's just,
The Becoming of Man or whatever scene where the like monkeys start using tools.
oh, yeah.
And then it plays that like classical song. I can't remember what it is.
So we're gonna say this, that we have 400 millimeters. Okay, and then we're going to apply a torque, and then the rest of it's gonna be 600 millimeters. All right. We'll call this A, fixed end. We've got a second fixed in here, which is gonna cause us a problem. Right? We have a torque being applied at B, and we'll go ahead and call this 200 kilonewtons meters. All right, and whatever this is, where is he? This also, couple of other things. The equipment can handle a twist angle of 60 millimeters, and its G is 80 gigapascals. All right, and so, and we'll call this end here C. All right, so let's go ahead and look at what's happening for our free body diagram. Basically, let's remove those supports. So when we remove the supports, we have our tube. Right, and what do we know about the tube? We're told that we have a 2 kilonewton per meter, twisting it that way, but here at A and here at C, we're gonna have to be going the other direction, correct? Because those are gonna be our reaction. Couple of equations we're gonna wanna use, all right? The first equation is our equation of equilibrium. And that is that when we sum our torques, they're going to have to equal 0. And the other is our compatibility equation. Okay, so when we sum up our phis, that's going to equal 0. Our angle of twist is then going to be TL over I sub P G. All right, so let's go ahead and split this into 2 segments. So let's split it into segment AB, this is B, and then split it into segment BC. Because what do we know? Based on this one here, though, we can add up our torques, can't we? So we're gonna have a torque at A minus the 2 kilonewton meter, plus the torque at B, that's gonna equal 0.
You mean torque at C instead of B? Since B
Yep,
is
torque
utility.
C. B is applied torque, right? Excellent. Is that Simon?
Yeah.
All right, so let's go ahead and segment this, and let's segment it at B. Yeah, that'll work. So our first segment for this, gonna have the end here, right? We're gonna cut it here. So this is A, we're short, a little bit short of B. So this here, I'm gonna call this torque A, which we've already done, right? There's a force coming off of here. And then this is gonna be torque from A to B. So torque A plus torque A B has to equal 0.
They're gonna be going the same way now?
Cause you're just shy.
Just
Just
shy
shy
of
of
where
your
B
actual-
is. Right, and then we're gonna, and then when we look at the BC segment, then it'll be, then we'll put it back in. So we know then the torque AB is then gonna be negative of the A torque. All right, let's look at our second segment, which is going to be much larger. It's the whole thing then. Because what happens when we look at what's happening here at C? I have to identify, so I've got TA. Now I have the 2, and then here we're gonna have TC, aren't we? So TC is gonna see what's going on with both the 2 and TA. And actually, let's cut it before TC. So we're gonna cut it here. So then we're gonna have a torque BC happening. All right, so we're gonna have TA minus my 2 kilonewtons, right? Plus my torque BC is then going to equal 0. So my torque at BC is ultimately then 2 kilonewtons minus TA. Now, you might be asking yourself, why are we doing this, crazy little old lady? Well, the reason why is because we have our angles of twist, don't we? So our phi, which has to equal 0 when we add them up, we're going to have the twist from AB plus the twist from BC. All right, let's put in our equations for these. The twist AB is going to be what? That's going to be the torque AB, the length AB over I sub P G. Plus, we're then going to have the torque BC, the length BC over I sub P G. All right, and ultimately then that is all going to equal 0. Now, even though we're given we can calculate I sub P, we're given G, would you agree if we clear the fractions, those are going to disappear for me? We could just make things a little bit simpler. Kate doesn't buy it.
You mean just multiply that?
Everything through by G, I sub P.
Yeah. Constant.
Okay, so we end up then with TAB plus T, or LAB, length. TBC, length BC has to equal 0. All right, and so if you missed it because you walked away or because Robbie is really angry and upset with me, I multiply because I offended him, or he's taking things personally. I multiplied it through by I sub P G. All right, the reason why is, what did we find? Oh, go back. All right, what did we find? No, that's not where I want to be. Oh, here we go. So TAB, that's negative TA, isn't it?
Yeah.
TBC is then 2 minus TA. And we also have those distances. Okay, because in my original drawing, they were 400 and 600. So let's plug, oopsie, wrong problem. So let's go ahead and plug that in. TAB, we found that is negative TA. My length of AB is then 400 millimeters. Plus T of BC, we found that to be 2 kilonewtons minus TA. And then the length of BC is 600 millimeters, and that's then going to equal 0. All right. Excellent. Let's move something. Well, actually, let's leave that there. So -400. We got to do some algebra. It'll be okay. Minus 600 TA is then going to equal negative, or we'll just leave it as -2 kilonewtons.
Millimeters.
Oh, you're right. 2 times 6.
But then we gotta convert it,
It's a,
right?
it's a.
Well, no,
It's a Newton meter, or
Yeah.
kilonewton meter.
this is a kilonewton meter, but look, we'll be okay. But you're absolutely right. 1200
Just a millimeter.
the millimeters are gonna cancel out. 1200 kilonewton meter millimeter. All right, so the reason I'm not fussing that much about the millimeters, right, is this is -1000 millimeters TA. That's then gonna equal -1200 kilonewton meter millimeter. All right, so Kate, if I divide both sides by 1000,
Oh, it cancels them.
the millimeters are gonna cancel for me. All right, so isn't this slick? So we get TA is then equal to 1.2 kilonewton meter. Now we can plug that back in. So, because what did we say? We said that TA minus 2 plus TB equals 0. So 1.2 minus 2 plus TB equals 0. So TB is going to end up being 0.8 kilonewton meter. Can you do what?
When you move the.
Oh, I'm sorry, it's not B, it's C. I'm sorry.
When you move the 1200 over the equal sign and then turn it positive.
It was positive, honey. Yeah, let's look at it, kiddo.
Right. Sorry.
That's okay. Sorry, the mom and me came out. Yeah, because it's positive here, so when I flipped it to the other side, it's gonna be 0.
Gotcha.
Well, Alex, send me an email when you know when Robbie, I will come watch Robbie if I can. But I can't at 10 o'clock. I probably can't be there till the early afternoon. What are you doing? Are you figuring out when Robbie's gonna go tomorrow? Are you doing the schedule instead of doing class, Alex? Hmm. Yes, I will come down at 1. All right. Shall we do a homework problem now that we have an understanding of how to do this? Now, the author, well, let me be quiet for a moment. So I will do my best, but no promises. I'll be the one in the crazy blue hat, so I don't get sun on my face. All right. Right, so we have a stepped shaft. How are we gonna treat the stepped shaft? We're gonna treat it as two parts, aren't we? Okay. And what's gonna be different? So we can't do the trick we did on the last problem is we're gonna have a different what between the first part near A and AC compared to CB.
IP,
The IP is gonna change.
we can't just cut out the denominator.
We can't just like ignore the denominator. I know, how sad, too bad, so sad. All right, the allowable shear stress in the shaft is 43 megapascals and maximum torque that may be applied at section C. Find the maximum torque if the maximum angle of twist is limited to 1.85 degrees and then we're given G in gigapascals. So if I assume everyone has access, or you can Google it and you'll see the solutions. But when you do this on an exam, I would like you to walk through it, okay, and actually solve it. Because I think it's pretty funny. The author is like using equation 3-49A. Oh yeah, like the students are gonna know equation 3-49A.
Yeah, when you like thumb all the way back and find it.
Right, right. During the exam, you're gonna be, oh, I need to use equation 3-49A. I don't think so. So here is our drawing, right? And we have some information about this drawing. We know that our diameter at A is 20 millimeters. Okay, we know our diameter at B is 25 millimeters. We know our length, I'm gonna call it AC, is 225 millimeters. Our length CB is 400, that's a B, and 50 millimeters. Okay, so all of that I pulled right off of the chart. I know my tau allowed, right, is 43 megapascals. And we know our G. So that's going to be 28 gigapascals. All right. Okay, so looking at this, we are dealing with torque and we are trying to find, what are we trying to find? We're trying to find the T naught. Yeah, okay, I guess we're trying to figure out what that T naught is going to be. All right, and our primary equations we're going to use is our equilibrium equation and our compatibility equation. All right, so what do we start with but our free body diagram? So we have, let's see, this is smaller. And then it's gonna go bigger. Oops. All right. So this diameter here, we're given to us is 20 millimeters, right? We have a torque that is applied and it looks like it's going in. And did I see that right? No, it's coming at me. So this one's coming at me, T naught. Instead of us being given that one, we're gonna wanna find that one. All right, if that's coming out, then this one has to go in and that's gonna be my TA. And this one is going to have to go in and that's going to be my TC. So. We then end up having, what, we're gonna have T naught minus TA minus TC has to equal 0. Okay, that's our equilibrium equation. Okay, so let's go ahead and figure out how A and B are then gonna relate. Do we need to relate them to each other, or can we just pull it off with the fees? Okay, that's, I'm just looking at where the author got his funky equations from. And that's interesting. All right, so let's look at our compatibility equation. Well, we know, hang on. We know tau, don't we? Correct?
Yes.
Oh, no, we gotta figure out the relationship between them. Yeah, I thought we could get away with that, but that's not gonna work. All right. So let's go ahead and let's figure out our fees also have to equal 0. So we're gonna have a fee basically from A. And we'll go ahead and just make all these positive. All right, so our A fee is then going to be T naught LA. So our A fee is gonna be our, no, let's cut it up. I just think it makes more sense. Let's see if we can get there. Right. So we're gonna do a cut before. So this is TA, which means coming this way, we're gonna have TAB, right? So TA plus TAB has to equal 0. I drew them in opposite directions. Did I do that last time?
I think so.
No, you-
No, I drew them in the same direction. Okay. So TAB is going to be negative TA. All right, let's look at then the second section, so to speak. So we have our small area, and then we're going to have our large area. All right, and if you remember, what happens when we do this is it's going to see all of the previous, for lack of a better term, it's going to see all of the previous ones. So it's going to see TA, it's going to see T naught. All right, and then we've done a cut job here. So we're now going to have T of B, C. All right, so we're gonna end up then with TA. I guess that should be negative, right? Oh, BC should be negative also. So we're gonna have negative TA plus T naught plus T of BC equals 0. So T of BC is then going to be T naught, TA minus T naught.
So on this one, like on your when you did the problem, the previous problem,
Yeah,
you had TBC matching TA, but in this one you have it opposing each other? Is that on purpose or is that like?
Oh, no, it should be matching TA. So TBC is also gonna be negative. Right, because these are reaction forces, so we're then gonna end up. So then TBC is then gonna be T naught minus TA. All right, let's talk about our fees. We're gonna have phi in the AB segment from phi in the BC segment. Both of those have to equal 0. And our equation for phi is then going to be TAB LAB divided by I sub P, and that's going to be different this time, G plus. All right, and then we're going to have TBC LBC divided by I sub P G has to equal 0. We know about TBC. So TAB is negative TA. TBC was then T naught minus TA. We know LBC. And we know we can calculate IP and G. We're given G. All right, excellent. Now, what will this do for us? This will give us a ratio between the T naught and a relationship between T naught and TA. All right, and then we can plug that back into our given shear stress, but we're going to have to figure it out for both of them. All right, so LAB. LAB is 225 millimeters, right?
Yes.
Oh, let's calculate our IP. So that's going to be pi over 32. The first segment, our AB segment, is
Solid.
it's solid. Yeah, so it's going to be 20 to the 4th.
Yeah, I think it is.
So stick that in your calculator.
$15,707 point. Just make it 15,708.
All right, and what is this one going to be? That's the second one has a radius of 25.
It's 38,349. Yeah,
So what is it? 38,000?
38,349.5.
32 comes about by it being a diameter.
Because we have radius, the diameter divided by 2 raised to the 4th power. Okay, gives us the radius to the 4th. So 2 to the 4th is where the 32 is coming from.
Gotcha, instead of just doing the
8 by radius.
Yeah,
by
or
radius, you're doing.
yeah, it doesn't really matter. Old habits die hard. I prefer to use, because I make lots of mistakes, if you guys have figured out. I prefer to use what I call original source material. So if it's given to me in diameter, I would prefer to plug in a diameter equation than to plug in a then to divide by 2 and make some stupid mistake somewhere. There are no stupid mistakes, they're learning opportunities, but. All right, cool beans. All right, and we have G, correct? So What do we end up with? We end up then with a negative TA. L of A was B is gonna be 225. That's in millimeters. All right,
Can't you just take G out, cause it should be the same for both?
Good.
yeah, we can do that. So then this is then gonna be over 15,708 millimeters to the fourth. So what, I don't know if you guys heard what Simon said. He goes, can't you just take G out? This is then gonna be T naught minus TA. Right, times our LBC, it's on the sheet of paper, Molly. 450. Right, divided by 38,349 equals 0. So what Simon was mentioning is you could just take the G out, or you would multiply through by the G. All right. Okay, so we can now solve for TA in terms of T naught, can't we?
Yes.
All right. So let's see, whatever, negative TA, right? I've got millimeters over millimeters to the fourth. I canceled out the G by sending it out. So it's gonna be per millimeter cubed. No, it's gonna go, part of that's gonna go away. It's in the G, isn't it? Gigapascals. Pascal's a Newton meter.
Yes.
All right, so we'll have our newtons, but the millimeters will disappear. So plug this into a calculator for me.
It's Newton meters squared.
Oh, it's Newton meters squared?
And you want 225 divided by 15,708?
Yeah,
0.0143.
0.0143. Okay, then 450 divided by 38,349.
That would be millimeters cubed.
That's gonna be 0.0117.
0.0117 T naught minus 0.0117 TA equals 0. I'm moving that to the other side. So now I need 0.0143 and 0.0117 added together.
Point 026.
0.026. That's then going to equal 0.0177 tau naught. Divide both sides. It's already after 5. What do we get per TA? In terms of tau naught?
0.045 tau.
0.045 tau naught. Okay. Now,
Yeah, it's negative.
oh,
TA
it's-
is negative. Or whatever, doesn't matter.
this came over and became, and is negative here. So I'm dividing by the negative, so it's gonna end up positive.
Take both TAs over, it's positive. To that. Positive.
My approach is not.
Right? Okay. So there's other stuff we need to get to today, but where can we go from here? We're after that tau naught, aren't we? And we know what? We know the max that tau A could be. Right, and so that's gonna be T sub A. And then I have it as 16 over pi dA cubed. Cause it's what, it's G,
TR over G. IP
yes,
for angle twist, right?
no, not angle of twist
Oh,
for tau. I'm looking for
There's
the,
another one. There's like a G.
Yeah, it's TR over IP.
yeah, okay. So it's TR over, well, let's write it out the way it's supposed to be. TA R over IP, correct? Okay, we know what this is, it was given to us on the previous page. But it was given, the max it could be is then 43 megapascals. Right, that's then gonna equal 0.045. R is going to then be, or T naught, sorry, R is then gonna be 20 divided by 2, all divided then by the IP. Didn't we already calculate the IP?
Yes. Of AB,
Yeah,
which is 15,708. Millimeters for the floor. I'm really trying to get these units down.
Yeah, they
It sucks.
okay. So, I'm thinking we need to convert some stuff around. So if we're looking at megapascals, that's gonna be what in terms of Newton meters?
6. What is it?
Wait, mega to Pascal?
Yeah,
6, 10 to the 6 Pascals.
pascals. Actually, I'm gonna write it as it's a Newton meter. 0.45, yeah, I am. And then we're gonna have this T naught, then this is gonna be 10 divided by 1,000. Divided by 15.7, or sorry, 15,708 divided by 1,000 to the 4th. Okay, according to this, you end up with a T naught of then 150 Newton meters. All right, now that's only one side, isn't it? You have to go through the same development, because I want to get into power generation. So you're gonna have to go over the same development for your BC. And then you're gonna get a T naught of 240 Newton meters. Which one is smaller?
150.
150. So this becomes our control. Right? So that's then the answer, but you do need to calculate it for both of your sigmas,
Is there a case where,
or both your sigmas, I'm sorry, both your T naughts, go ahead.
is there a case that your T naught in a bigger diameter would be smaller than your smaller diameter? Like if it would be, so that it doesn't matter that we calculate the second
If your
part?
G is different.
If your
Yeah,
G is different?
Yeah.
yeah,
That's material property.
right.
It's material property and like surface area.
Right.
All right, so I've talked a lot these guys are dying in here. I'm sure Robbie is totally cool and ready to go. Let's take like a 10-minute break.
Yep.
Go outside, get yourself some water, and then we're gonna come back and we're gonna do power generation.
Without.
Be
Work overtime.
Let me hit the restroom. I'll be right back. Right, so what's up? Yeah. What about the homework? It says, for example, 1 through 1, but in the book it's 1.3-89. So let me look at that.
Professor,
Yeah,
so the homework on D2L, it says do questions 1.1-1.3, but
mm-hmm,
in the book it's 1.3-9-5. Even the homework one set you uploaded, it's the same thing. It's 1.3 dash something. It's not. So I got confused on what exactly I should upload after the homework set one, and to which homework link do I upload it to?
oh, where do you upload it?
Yeah,
So,
because in the book it's different than on the asked in D2L. So in D2L it asks for 1.1 and then 1.4. But in the book there's no 1.1-1.4. It's 1.3 and then dash something per question.
okay, so let me. So if you go into D2L and you go into syllabus,
Mhm.
right? And then you go schedule of work, which is horrifying because we're so far behind. Okay, so, oh, this is the wrong class. So the section is 1.1 through 1.3. But then you will see you'll have 1.3-7, 1.4-4. So these are directly out of the book. So
Okay.
you have 1.3-8-9. I don't see that, but this is the sections being covered. And then these are the associated homework problems that go with it.
Oh, okay. So I gotta look in syllables and then correlate it with the homework I gotta upload for that specific section.
Right, so this section, for example, has 1, 2, 3, 4, 5, 6, 7, 7.5 problems. So you would then upload, you go to homework. When you go to homework, these 7 problems is what you would upload. This is the section. These are then the problems over here.
Okay, got it.
All right,
Thank you.
you're welcome. Stop being stupid, get back here. All right, so, we're gonna start in 3.7 through 4.1. This is, by the way, the section, well, I guess it's not 3.7 through 4.1. 4.1 through 4.3 should be review. So should. Yeah, it's shear forces and bending moments. We will go over it. So should chapter 5 is where things are going to get more complicated, and we're gonna start gonna start applying those. So you two, we will actually be doing this on Monday. So what I'm calling review in here tonight, you will physically experience on Monday. Wait, we did, no. Did we do 4.3 yet? No, we did 4.3. We need to do 5.3. So we'll finish it on Monday. Okay. So 3.7 talks about power transmission, and we will go ahead and look at that. And then we will talk about beams and our beam review real quick. Now, there is a section in the book, chapter 9 is how to design a beam. And I will be honest, if you Google design a beam, a ton of websites is going to pop up for you. So instead of me explaining the old way to design a beam, I'm thinking what I might do, believe it's chapter 9. I'm thinking what I might do is instead give you a beam to go do a design on using the internet, so to speak. All right, so let's talk about how power is transmitted. What is ironic is the dynamics crew finished this week, which is kind of funny. Oh, I'm sorry, I made that super small because it was a little blurry and it was bothering me. All right, so we have a motor. The motor is spinning a shaft, correct? On this, we have some things labeled. So let's talk about what those are. And we'll then talk about power. And do a problem, okay? And then we will do some review stuff on beams. And then in class, folks, I have a little quiz for you. No, I don't. Do I? Yeah, I do. All right, they're looking at me with shell shocked looks. So omega here is my angular momentum. Or not angular momentum, I'm sorry, angular speed. Sorry about that. Dynamics was calculating angular momentum. All right. So omega is our angular speed. The T here, we know T, this is our torque, correct? So this is inside an engine and it is spinning. Our angular speed, I want to make sure this isn't, because I always think of power in terms of work. And I've got, based on my notes, it's a little different. Let me double check the book because it just could be my sloppy handwriting.
What are you looking for again?
Yeah, it's work. Never, I've got it. Okay, so what we're gonna want to look at is we're gonna want to figure out and calculate power. And power is the change in work with respect to time. All right. When we are dealing with this, with a rotation or a torque going on, our work is defined a little bit differently. Here, work is going to be defined as torque times psi. All right, I've just introduced a new equation. That always causes confusion, right? Psi is then the angle of rotation. So when we calculate power, technically, we're gonna write power is the change in work over change in time. That's then going to be, we're gonna have torque psi over change in time. The torque is gonna be supplied by some motor. So it's going to be constant. So we are looking then at how the angle of rotation changes with time. Right? Now, this here, right, an angle changing with time. And notice I said omega was angular speed, correct? So if I have an angle changing with time, this is going to be omega, isn't it?
So it'd just be T omega.
So power for us is going to be the torque T omega. All right. Omega, by the way, is going to have units of radians per second. All right, so that's what's happening. That is usually not how things get expressed. All right, instead, omega, our angular speed, we're in radians, so that's going to be 2 pi f. This f here is then the frequency. All right, it is usually in hertz, not the car rental place, but it's in hertz, which is then inverse seconds. All right, so if I plug that in, I get almost get the equation that the author likes to use. So that's 2 pi f. And then we're going to have T, our torque. Okay, so if you think about frequency, frequency is how often it's going around, correct? Yep. All right, so that is the number of revolutions. And that's then going to be divided by 60, right? Because this then, instead of giving us per second, we're then in RPM, or revolutions per minute. All right, and when you drive your car, you see your RPM, don't you? Right, that's what it's measuring for you. I don't know why we have that dial anymore.
Which one?
The RPM.
Yeah, tachometer. I don't know.
I don't know either. I think it's just habit now because when you drive a manual car, that helps you know when you need to shift. But in an automatic,
Yeah, but I mean, if your transmission is not working properly and you're just rev bombing the shit out of it.
Or you're like telling.
Yeah,
Yeah.
you can still gauge how hot or much.
I guess so.
Modern
I guess it
cars-
can give you an idea of transmission failure.
Yeah,
Yes, I think it's
But-
if you notice you're
jumping up and down.
yeah
It's jumping
fluctuating
around.
in RPMs, you could figure out something's wrong with your motor.
Yeah, maybe. I don't think we're smart enough to do that anymore. Because people don't work on their cars anymore.
I think it is. Well, it's still a requirement.
a requirement to work on your car?
No,
You don't need
You
a
don't,
jack.
tax aren't required anymore.
really?
Yeah, some modern cars aren't needed.
Well, I get like a electric car, doesn't have tax.
Still, you can gas when you drive.
Alright, so I'm sorry, I got distracted, but this time I actually,
Are you for? That is ridiculous.
but on the other hand, I got distracted, but Simon went down the primrose path with me this time, so it was okay. Alright. So Amelia says that she has driven her car too hard before and redlined it before it had time to switch gears. Yeah, that's not a good idea.
It's awesome.
No, not
That's
not Amelia, me, Austin.
Really, drag racing.
Alright. My daughter did some time trials 2 weekends ago at the track, so, and she managed to break something. So. Alright. Okay. So let's go ahead then and try one of these problems, so you can say that you have seen it. Alright, so we have a propeller shaft of a large ship. 18-inch diameter outside, inside diameter of 12 inches. So this must be the drive shaft of the ship, not really, oh, propeller shaft, yeah, not the actual propeller. The shaft is turning at 100 RPM. What is the maximum horsepower that can be transmitted without exceeding the allowable stress? All right, so we are gonna have to back up and figure out our equation for horsepower. And the way we do that is a unit conversion more than anything else. So the horsepower is 550 feet-pounds per second. All right, so, and then we're talking about the rotation speed of our shaft. So we're missing an equation here, which I skipped over. Our horsepower is going to be 2 pi nt divided by 60. Now 60 was seconds. We have to multiply that then by 550, right? And that's going to turn it into horsepower for us. So this becomes then 2 pi nt over 33,000. All right, so this problem isn't too bad. Let's write down what we know. All right, so we know we have an outside diameter of 18 inches. I think he calls it D2. Anyway, that's 18 inches. We have an inside diameter of 12 inches. Now, when we have an outside and inside diameter, what is that telling us that we're going to want to figure out? I sub P, right? That's where those are going to come into the equation. All right. We then have, we're told our tau max is 4,500 PSI. All right, and we want to figure out maximum horsepower. So we want to find this H value. Now, I believe N is given to us, isn't it?
Not sure.
No,
Yeah, the shaft is turning at 100 RPM. So N is given to us. All right, so N is then going to be 100. All right, we have, what do we know? Well, we know 2 pi. We know n. What are we missing? We're missing t, aren't we? How can I find t? I feel like we've done this whole thing. We have.
Shear equation.
Right, our shear equation, the fact that tau equals TR over IP. That's what the day is being brought to you by. All right, so our IP, we're gonna have to calculate. Our R we have and our tau max we have. So let's start in on our IP. IP is then gonna be pi over 32. And then we're gonna have D2 to the 4th minus D1 to the 4th. Or the outside diameter minus the inside diameter. So how pi over 32 is then gonna give me 18 to the 4th minus 12 to the 4th. So the answer is then 8270 inches to the 4th. Is that what you got when you guys plugged it in? Is that what you got, Simon?
No, I'm doing,
Oh,
still calculating.
Alex, are you still there? Is that what you got?
Yeah.
Alex, can I wear jeans tomorrow or do I have to look professional? All right, so that's per square inch, that's in inches, that's all good. All right, so let's go ahead then. We know this is going to be. That's weird. Oh, I see what I did. Okay, this is gonna be 4,500. That's gonna equal T. We're then going to have our diameter, our big diameter, because that's where we get more of a force coming in, over 8270 inches to the 4th. All right, so multiply, divide by 9. And I believe we end up with 4.135 times 10 to the 6 pound inch.
Yep.
All right. Okay. Now if we go back, this T here is, I have it in pound feet. See if that makes sense. Well, let's go for it. So we're gonna have to convert that guy, aren't we?
Well, your horsepower is feet, right?
Yeah, it is in feet. So let's go ahead and convert this poor kid. So we're gonna have 4.135 times 10 to the 6 pound inch. All right, and then in 1 foot, we have 12 inches. Right, and so that's 344,590 pound feet. Now, we can plug this in and get our horsepower. All right, 2 pi, 100 RPM, 344, 590 over the 33,000 to turn it into horsepower. And we end up with 65, 61 horsepower.
Yeah,
Right. The second part of this problem is actually, let's just understand, well, it's silly. If the rotational speed of the shaft is doubled, but the power requirement remains unchanged, what happens to the shear stress in the shaft? So our horsepower is going to stay the same from part A. Rotational speed is double. What does that mean? Which variable n is going to change? So for part B, right, h is 2 pi n t over 33,000. This is going to be then 65, 61, 2 pi. The difference is my rotational speed has doubled. So n is no longer 100, it is now 200. Right, and then we end up with, at one point I got a torque of 172,295 feet pound. Right? So hopefully these problems won't be too bad. All right, okay. Okay, so at this point, we are going to do beam review at the speed of light. Now, if you didn't like doing this chapter in statics, you're going to have to pay close attention. Simon can space out if he wants to. But chapter 4 is, for lack, it's basically review. It should be a review. All right, so we're moving into chapter 4, and we're going to talk about beams, and we're going to talk about their reaction forces. All right. Now, the lads have learned this part. We're going to make it a little bit more complicated, but not much. All right, so if we talk about our reaction forces, because we're going to get into those moments, and then we're going to actually start analyzing those bending moments instead of just graphing them. So reaction forces. Let's see if you guys learned anything this week. First one, let's do a simple beam. All right. Okay, and let's say we've got a couple of applied forces happening on my simple beam. Or we don't.
the red one doesn't work.
Figured that out. That's okay. This morning in B312, nothing worked. The markers would not work at all. All right, so what type, Cade, reaction forces are we going to have here at A?
You're gonna have a Y and an X. Because it's a pin.
Alex, do you agree? Alex, did you take statics from me? Yes, you agree, or yes, you took statics from me? Yes and yes. Okay, I thought so. All right, so this one's then only going to have a BY, correct? All right, so that's our simple beam, simple supports. we spend a lot of time in statics dealing with that simple beam and those simple supports. Okay, the second type of beam, and we're gonna give this one a formal word, so to speak, is the one that's embedded in the wall. So that's gonna be a cantilever beam. All right. So this is embedded in a wall. What type of reaction forces does it have? We'll call this point A.
XY moment.
X, Y, and then it has a reaction moment. Now, if you had to put up with me for statics, I do show you this and I show you an example of this, but I don't actually think you have any in the book. All right. So if it's embedded in the wall, oh, I almost kind of started labeling things with an R. By the way, U of A people, Robbie, Brock, you folks, I always draw reaction forces in compression. I'm assuming I was beaten as a child or something, but I always draw reaction forces in compression. All right. The other beam that's kind of like a cantilever beam is then, and so these are the three that we're going to see in this class, is then a beam with an overhang. I do believe, I remember doing a problem like this. All right, so if we have a beam with an overhang, we're going to have, we'll call this A, we'll call this B. All right, and the difference is, what are the reaction forces going to be at A? Tyler?
It's X, Y, and
Right. It's going to be XY because this is a pin connection. What are we going to have at B?
Y.
Okay, BY. Now, the difference is that since it's an overhang, there can be some rotation in there. So there can be a potential moment happening. All right. All right. So, as I said, your guys are getting like 3 chapters of statics in 10 minutes. All right. Any questions on this? Give me a 4 if you're doing okay and you're still with me. Probably need to take attendance. Supposedly I have 8 of you. I'm only seeing 4 pop up. And Robbie and I wasn't counting the Robbie Alex team. Okay. So, type of loads. Loads is another word for saying applied force. The first one is not realistic, but we spent a lot of time in statics messing with it. And that is when it is concentrated. Okay, so if I have a beam and it only has an applied force at a single point, right, that is going to be concentrated. The second one, which we're going to spend a lot of time with in this class, Elizabeth gives me a 4. Oh, is Elizabeth in the room with you? Okay. She's taking solids? I thought she only took fluids. It doesn't matter. I'm confused. It's all right. It happens all the time. is then the distributed load. Okay, distributed loads we'll be going over on Monday. All right, so this is sort of a preview. So let's review a couple of distributed loads. If we have a distributed load, looks something like this. Right, and we're told, we're given the intensity is 50 pounds per foot. And this is 5 feet. Could you tell me what then the point or concentrated single force load is gonna be?
250 then.
Okay, so it's gonna be 250. And where is it going to happen?
Centered on the load.
Centroid on the load. So it's gonna happen here. Oh, the red pin doesn't work. It's gonna happen here at 2.5 and it's gonna be 250 pounds. Do you remember doing these, Alex? Oh, Elizabeth is a special guest today. All right. So she can tell me if I'm teaching this wrong compared to U of A. Right, we also have loads, right, the other primary one we do in statics is when we have triangles. Right, and so the intensity of the load or the single force is going to be then 1/2 base times height. It's basically the area of a triangle instead of area of a square. All right, now what we don't do in statics, which we will be doing in here, let's say we have a load that looks like this. How am I going to figure this load out?
By integrating it.
We're gonna have to integrate. So we're gonna have to integrate to get the single force, get area under the curve. We are also going to have to integrate in order to be able to figure out where the centroid is. Okay. The other one that we may see, I can't remember, is then if I have two forces going like this, what is this?
Force pair.
Force couple. Close.
Speaking of statics. Yeah, sorry, I already did that. Pretty good stuff.
All right. You can also have applied moments put in. All right, so let's go ahead then and review internal forces. And then we'll do a problem. And then we'll probably, I got a quiz for you guys. But I'm worried that you were busy taking your exam. Should I just send it home with you?
So I would appreciate that.
Okay, but you got, I know Tyler's keeping up with the homework because he's the homework king. Are,
In this class. I need to,
we need to do a little bit of homework. Okay,
it's been rough.
that's okay, you've got a rough semester.
Well, yeah.
Part of it's my fault because I'm the one who said it was okay for you to do this. So let's go back.
Very true.
What'd you say?
That's very true. You put that in my ear, I was like, ooh, that sounds cool.
And then he
Not
put it
my
in
fault.
ear.
Yeah,
Okay, so let's go ahead and take a look at our beam. All right, and let's say we have some forces on this beam. Okay, so I'm applying some forces. We also have some reaction forces on the beam. What reaction forces are we gonna have at the first one?
XY. Yep, boy.
It's funny, what's been happening to I as well.
What
The knee just pops.
Oh,
you
well,
walk on.
no, you break the plane or something, it pops up. Okay, so this is then going to be AY and AX. And here we will call this BY. All right, so unfortunately, folks, this is chapter 7. So you're a little off from learning this in statics, but it's not that bad. When we're worried, these are all external forces. Do you agree? Elizabeth, are these all external forces? Alex isn't paying attention. Yes,
So
they are.
the shear stress, that would be an internal, right?
Correct. That's going to be an internal force. So how do we get our internal forces? Well, we're given a point and we're going to cut it. Right? So we're going to imaginarily cut our beam in order to solve for it. When I cut it at a particular point, I still have my reaction forces. Right? I still have my one applied force. But now we're going to deal with our internal forces. There are 3 internal forces. Okay? One of them is shear. So this is going to be shear. All right. We then have the force coming through here. This is going to be my axial force. All right. And then we are going to have an internal moment. So those are the 3 forces we're going to have to look for: shear, axial, and internal moment. Okay. All right, let's do a problem. We're going to have to go over carefully in December. No, it's not going to be that long. Bending moment diagrams. Is that on your? So my hope is that the sub can do bending moment diagrams with you and moments of finding centroids and moments of inertia. Oh, I didn't give you one of these problems. All right, I'm gonna have to fix that, but I'll give it to you anyway. All right, we want to determine shear force and bending moment at a cross section located 18 feet from the left-hand side. All right, and so over here at 18 feet, we're going to cut this guy. What's the first thing we need to do?
Free body diagram.
Free body diagram. We're also going to have to figure out what these point sources are. So we will start with our free body diagram. Right, so here I have AY. And here I have AX. I've got this force here is 400 pounds per foot, so what's the applied single force gonna be? All right, it's gonna be 4,000 pounds occurring where? All right, it's gonna occur 5 feet from the edge. All right, then we have B hanging out over here. It's a roller, so it's only gonna go BY. Then over here at C, we have 300 pound-feet for 6 feet, so that's going to be 1,800 pounds. It's gonna occur 3 feet off the edge. And it's pointing up. Why? And this is a little different than the statics book. Why is it pointing up?
Pulling instead of pushing.
Right, because those arrows are going up.
Cause the force goes up, cool.
Because that force, it's
Checks out.
got a force coming up. It would probably make more sense to draw it down here, to be honest, but. All right, so we're pulling it up there. All right, so what do I do next?
Solve your reaction force.
Solve for our reaction forces. How are we gonna solve for our reaction forces when I've got two AY and BY?
A moment.
Take a moment. Where should we take it?
Excuse me?
What?
You make the button B.
Yeah,
Oh, where should I take the moment?
from A.
Busiest point. By the way, we can write this down. F of X equals 0. So A of X is gonna be 0. All right, let's go ahead. We're gonna take the moment about A, which equals 0. So that's gonna be 4,000 times 5. And that's clockwise. Did I do that right? So it's gonna be negative.
Is indeed clockwise. Right?
All right,
Yeah, wait,
Yeah,
Yeah,
it is.
all right. Thank you for your words of encouragement and support. All right, then what are we gonna have? We are then going to have BY. BY is off by 20 feet and that's gonna push it clockwise. All right, and finally, we have 1,800. 1,800 is also gonna push it clockwise and it's off by 3 on the end. So 10 plus 10 is 20, 6 is 26, 6 is 32, minus 3 is 29. Did I do that right?
and
Oh.
20,
yeah, it's 29.
It's 29.
it's 29, yeah.
I think it's 20.
Is it 29?
It's 29.
It's 29.
I'm pretty sure it's 29. 29.
All right, so stick this into a calculator for me. There's thinking, calculating in the classroom.
At school, I just asked.
That's negative 1610.
So BY came out to be negative 1610.
Yeah.
Yeah, but I mean,
No, that's good.
No, that actually makes sense. Right, because it's gonna have to counteract that moment.
Yep.
All right, so BY is actually pointing this way. Red does not work in this room. Point of information. All right, can I now figure out what AY is, which is why I went through this whole
yes.
scenario. So if we sum in the Y direction, we're gonna have AY minus 4,000 minus 1610 plus 1,800 equals 0. So that gives me what, negative 56, and then I'm adding 18, so that's what? 36, what is it?
3810.
38. So AY is equal to 3810. Right, so that is the first part of this exercise. All right, now we're gonna cut it. So the author told us to cut it at 18. So let's go ahead and cut it, and I'm gonna go ahead and do the shear and bending moment diagrams. These are gonna become a lot more complicated very shortly, because there's a lot more going on. So we're gonna copy this. Give myself a new sheet. All right, so we're gonna cut it here at 18. I want to redraw my free body diagram based on what I now know. I'm cutting it, so the way I symbolize cutting it is it gets a jagged edge. So jagged means we're cutting it. We know we have A here. You know, okay, I know I have A here. This A, what did we just find it? 3810?
3810. AY.
Yeah. AX is 0.
X is 0.
Okay. 400 is over by 3, and we said this was then 4,000. Correct? And this is offset by 3. So if that's over by 3, our cut is then over by 15. All right. At the cut, how many forces do we have at the cut? 3. We're going to have shear. We're going to have axial. And then we're going to have our interior bending moment, which is what's going to become a lot of fun for us. All right, so let's go ahead and calculate our shear. Now, I'm going to do something a little, your author does this, right? This is the calculations at 18 feet. So he makes shear B sub 18.
Okay.
All right, if I sum in the y direction, this I have pointing down, plus 3810 minus 4,000, that's going to equal 0. So negative v sub 18 is then going to be, what, 190? It's going to be positive 190, isn't it? So that means the way I drew it, v sub 18, my shear is then going to be negative 190. No cause for freak out. What does that mean?
It's just reversed in your diagram.
Right, I need to reverse it on the diagram. So here is my shear at 190. Axial, what is my axial force going to be for this? Right, if we sum our forces in the x direction, then it's just going to be 0, correct? We okay? No?
Okay. Now we're good. Yeah.
All right, we then need to figure out what is happening to our moment at 18. Now, the moment at 18 is going to, you can think of it as, I'm sorry, the word just fell out of my brain. As if you're finding a resultant moment. Okay, so let's see, what is 3810 going to contribute to the moment at 18? Is it perpendicular?
It is.
So yeah, it is. All right, so that means we're gonna have 3810 times 18 feet.
Because
These-
the axial and the shear would cancel because you're taking the moment about 18.
Well, since you're taking the moment at 18, yes, you wouldn't worry about the axial or shear contributing to that moment. It is going,
Negative.
it's gonna be negative. All right, then what are we going to have? We are then gonna have that 4,000 force times 15. That's gonna be counterclockwise. So this is then gonna be plus 4,000 times 18.
Times 18,
No, times what?
15.
15. Right, and that gives us a moment of what?
Negative 8,580.
You did not just do that in your head.
I did not, you're right.
What did you come up with?
Negative 8,580. For the calculus.
Okay, did everyone else get 8,580? The author got 16,000. Negative 380, 10 times 18. Plus 4,000 times 15.
Positive. See what happens.
Okay, I'll buy it. What else? What numbers are you guys getting online? We're getting really tired here. You
Yeah,
got the
same
same answer. So what was your answer?
Negative 8,580.
8,580.
Right, and that's then going to be pound feet. All right, so we need to talk about the sign on this. If we calculated out that the moment occurring at 18 is going to be negative 8,580, correct? But what is our reaction moment going to have to be then?
Opposite.
The opposite. So it's going to be 8,580. Okay. All right. Let's talk real quick, probably too quick, about our shear and our moment diagrams. Yeah, I guess we can do that. I'm not going to get very far on it in 10 minutes. The thing is that so chapter 4, as I said, should be review. It's when we get into chapter, I don't know where it is, where all of a sudden the diagrams get really ugly.
Like 4 or 5.
No, I'm not seeing any ugly diagrams in 4. 5 is just beams with axial loads. I think things might get ugly in 7.
That's December's problem.
That's what?
That's December's
Really? Alright, so let's talk about how these work out. Alright, let's back up. This is the way I like to do shear and bending moment diagrams. This is the way I teach it over here in the community college. Let's say I have a reaction force here of 200. Let's say I have an applied force here of 400. So, and this is over by, I don't know, 5, and then we're gonna go over by 10. And we have a reaction force over here. If that's 200 and that's 400, this has to be 200. Okay, do we have any internal forces off the ends of the beam? No. The way I teach this, and this is a basic one, is I'm going to draw a line straight down. We'll start with our shear diagram. All right, you're going to follow what you see here. So we're going to, if I am like one itty bittiness, one hair length in, it's going to see what? It's going to see a positive 200, isn't it? This is then my first critical point, because that's where the next force is. So it's going to see 200 until it gets to this point here. This is 5 feet. And at that, it's going to have to drop how much? 400, which is then going to put me here at negative 200. We then head over, and we're going to come back at the end of the beam to 0. So sure enough, that's then going to go up 200. These should always end at zeros. So this is, if we think about this in terms of area under the curve. All right, so we have our shear diagram. The moment, the shear is the derivative of the moment. So I need to do what then? I need to integrate it. So integrating gives me the area under the curve. This line here, right, if this is 200 times 5, that's going to be 1,000, isn't it? It's in the positive region. And you guys can skip class during chapter 7 because you'll be pros at this. So I'm here, okay, and this is then going to be at 1,000. If we have a straight line and we take the derivative of it, we're going to get a line going like that, aren't we? All right, we're then going to have a negative slope. This, I said this was 10. So 200 times 10 is going to be 2,000. Wait a minute, what did I do wrong? Because we're going to have a negative slope. Oh, we're going to have a negative slope, but it's going to be 5 times 200 is going to give me 1,000. That's going to put me there, right? We should end up back at 0. That's why I'm fussing. What am I doing wrong, Simon? Yes, you do.
Should
We
be,
just did
it should
this.
be. That's the thing, is it shouldn't be balanced. Well, no, it should be.
No, the area under this curve is going to be 1,000. Right? My problem is the area under the next curve is going to be negative 2,000, which is going to put me here.
Yeah. Isn't it because you're already like at the 0 point, you're starting at 200? Right, so it'd be going up from 200 to,
So it'd be 1,200 up,
right, cause you're drawing it essentially that you're
starting from 0
starting
to
from zero.
your
Yeah,
max.
like you're think, like you have it drawn that your initial slope should actually be at 5 foot instead of the other way.
Oh, okay. The result should be. We should end up back here at 0. Right. So, your quizzes become take home. Please, you guys do some homework. So expect the exam to cover 3.1 through 4.5. I will have her do a bending moment exercise with you on Thursday, if I have a sub, and do centroids and moments of inertia on Thursday. But since I'm not gonna get to spend time with you on them, I will not put them on the exam. Does that make sense? Is that fair? I will post an exam review video. I'll come out tomorrow. All right, so here's the ones in the classroom. I don't know why it says KK. But that's all right. Which one? Oh, excellent, yeah. I thought you were gonna argue about a grade.
Oh, well, you know, that comes after.
Once
the
it is-
fact. Yeah, that's right, I would have my words to say.
I'm sure you will.
Just about separate paper.
That's fine. You always keep me on my toes. I appreciate that. All right, guys. Get the take-home exam done. You have a take-home quiz that'll be due next week. This is the 3.8. You will do an in-class exercise on shear and bending moments. I need to take attendance. It's well that Alex left, but I need to take attendance, so I'm not in attendance jail.
Without my helmet.
I'll be in attendance jail anyway. But I might as well stay out of it for a little while.
Thank you, Dr. Minky.
Yeah, thank you. We'll catch you next time.
Oh,
Say
yeah.
it on the chat, and then you guys can go.
We won't be, wait, you're not gonna be here.
No, I'm gonna be here
Thursday.
next
Okay.
week. I fly out Thursday is the problem. This is the cancer-free celebration trip.
Yeah.
Alright, well, you have a good weekend. Enjoy your weekend.
I'll see you Monday and I'll see you Tuesday. I will not see you Thursday.
Right on.
All right, once you've said here, I can get your attendance taken from the chat. Feel free to enjoy your evening. Get those turned in, folks. Declan, are you online? I don't see you. Rasul. All right, I will see Robbie tomorrow. You guys, good night. You're dismissed.